So, my name is Niklas Frykholm. I'm going to talk about another game engine. It's all game engines today, which is called the Stingray game engine, which is what I'm working on, and we're also using Lua in our game engine. And I'm going to especially focus on the things that we do that might be considered a little bit weird, but we do it for performance reasons and other reasons. So hopefully that will be interesting. This is our engine. It's a 3D game engine, so we're driving for like the full AAA, the AAA market as it's called in the game industry. That's like the big games like Battlefield and stuff like that, but also supports simpler games as well. It's a multi-platform game engine, so we're targeting PCs, mobiles and consoles. We started the development here in Stockholm. It was just me and one other guy who started working on it in 2009. And we were actually acquired by Autodesk in 2014. So this is now Autodesk's official game engine, and they're selling it as a product. So I'm just going to show you some pictures of games that have been made in this engine so you have an idea of what kind of games you can do. As you can see, there's a pretty big variety of different games. We have puzzle platforming games, we have RPG games, first-person games, third-person games. Just to show you that it's not locked down to one particular type of games. You can make a lot of very different games with it. It's also used for some non-gaming applications like augmented reality. It's used in home decoration projects, some architectural visualization projects as well. So when you're programming games, this has been touched on a little already, but when you're programming games, you typically have two very different kinds of code in your game. You have one part is sort of what we call the engine code, and that's low-level code that needs to be really, really fast, because games, as all the previous speakers have said, performance is really important. Games still compete pretty much on performance. If you're not performant, then you don't have a good game engine. So this code needs to be really structured, really fast, multi-threaded, and so on. And we also this code is also pretty much work to write, so we definitely don't want to rewrite it for every game we do. We want to be able to reuse this code for multiple games. Then you have another kind of code, which is sort of the gameplay code, we call it. That's the code that's specific to one particular game. And that code tends to be much more high level. It tends to be pretty messy, because as the previous speaker mentioned, you often have a lot of special cases, like, well, we have a lot of enemies that are like this, but then we have this special dragon who has this special behavior that doesn't fit in with the other stuff. So it tends to be messy in that way, and difficult to structure as rigidly as your engine code. And it's also something that you need to be able to iterate over quickly, because the games change, the requirements for the game change, and so on. And of course you want to rewrite it, at least most of it, for every new game, because every game is different. So in some engines they write this gameplay code in C++. The engine code is always written in C++, almost, because we need the performance. But in some engines they also write the gameplay code in C++, and I think that's very problematic for a bunch of reasons. Because C++ tends to force you into a very rigid structure. You tend to get sort of locked down into the classes you create, and it's hard to change that around for some reason. I mean, you can rewrite your classes, but it's somehow the mindset that it puts you in, it feels like it locks you down. And of course, C++ is also very punishing. If you make mistakes, like you make some mistake, you get an access violation and your game blows up. So that also prevents you from doing experiments and changing stuff around and iterating. And you also have pretty long compile times. We try to keep them as slow as we can, because we like to iterate over the C++ code quickly as well. But still, you're probably talking at least a minute of compile time for compiling your C++ code. And for experimentation, you really want to change it quickly. Another problem that is perhaps not super obvious is that when you have the gameplay code and the engine code written in the same language, you get to get the kind of abstraction leakage between these two words, which by that I mean that these messy concepts that you have in the gameplay code tend to sort of leak down into your engine code that you really want to be nice and structured. So maybe your engine code starts to talk about things like weapon slots or bullets or things that really the engine shouldn't. That's stuff that's particular to a specific game. It's not something that belongs in the engine code, because not every game is going to have a weapon slot or bullets or something like that. So this can really destroy your engine code if you're not careful about it. So our solution, very similar to default solution, is that we have separated it into two words. We have the engine code, the fast code written in C++, then we have the gameplay code written in Lua. And all the things that are like game objects that are specific to a particular game, like a car, a player, score, or something like that, that only exist in Lua. C++ has no idea about the thing like a car. The C++ only deals with much lower level objects like a mesh that needs to be rendered, or a sound that needs to be played, or an effect or something like that. And we get this nice language barrier that prevents this abstraction leakage. It prevents the gameplay concepts for leaking down into the engine code. And the nice thing about this as well is that this separation allows us to change the engine code freely. As long as we keep the Lua API the same, we can do whatever we like to the engine code. We can, for example, take a system that was single-threaded and make it multi-threaded behind the scene, behind the Lua API, and Lua won't even be affected. Now, if the gameplay code was written in C++, this would likely disrupt the gameplay code, and they would have to rewrite everything. But we can do it without changing anything. And it also allows us, which we use a lot, because we like it, it allows us to push all the tricky decisions to the Lua code. So if we're in a situation where, should the engine do this or should the engine do that? There are a lot of situations when there's no good clear-cut choice. We can just say, well, they can decide that in Lua and call whatever they like. So whenever we have a hard problem, we just say, well, they have to solve it in Lua, which is nice for us. And all of this together allows the engine to be very data-driven and allows us to use the same engine code for very different games. As you saw, we had very different types of games. All of these games are using the same C++ code. All these differences are only in Lua. There's maybe like 1% C++ difference. They've written some special stuff where they need a really high speed, but most of it's exactly the same C++ code for every game. So why Lua? I'm not going to dwell on this because it has been talked about already. It's a small, simple, powerful, flexible language, fast, dynamic, really nice. The main alternatives that we consider to Lua is C# and JavaScript. I would say that the biggest advantage of C# is static typing. You can have different opinions about dynamic typing and static typing. In my mind, I really like dynamic typing in the beginning of a project because I feel it allows me to experiment and try things out quicker. But once the project gets more locked down, I kind of like static typing because it allows me to refactor things and not be unsure about, well, have I destroyed something somewhere? Do I really have complete test coverage? How will this affect everything? So for those reasons, I like static typing in the final stages of a project. Another main alternative would be JavaScript. I would say that JavaScript is like poor man's Lua. I mean, JavaScript and Lua are almost the same language. It's almost the same. Beneath the surface, it's almost the same language, except that JavaScript has a bunch of stupid stuff that you don't want and you don't need. The only reason for using JavaScript is it has bigger momentum than Lua because it's the language of the web. So it's more people know it. It's a lot of people working on VMs for it and all stuff like that. But Lua is a better language. I mean, no doubt about that. I wanted to show this is just an example of what the code might look like. So we have global functions that get callbacks from the engine, and we just have a few of these. We have an init function, an update, a render function. So the engine calls those, and from there on, it's all up to Lua. So Lua can sort of create worlds, create objects in those worlds, draw those worlds, handle keyboard presses, and so on. yeah, we use Lua for all the gameplay code. We don't use Lua in our data files, like in our definitions of levels and so on. So you could ask, why don't we do that? We could use Lua even more and use it for the data as well. After all, Lua is pretty great as a configuration language. Well, the main reason is that in our data files, we don't actually want that full flexibility, because the people who will be editing the data are not programmers, so they won't be working in a text editor. And all the nice features that you get by using Lua as a configuration language, that you can have a while loop, for example, in your data file and have some kind of procedural data generation. All that doesn't really work if you want to put an editor on it, because the editor won't understand your while loops or your functions in your data files. So because we want editors for artists, we want a simpler format for our data files, so we've gone with JSON. We could use like a stripped down version of Lua instead of JSON, but at that point there's not much difference or point to it, so it felt better to use more standardized thing like JSON. We also have a visual programming environment, because we want to expose some of sort of the advantages and possibilities of programming to people who are not programmers, like artists. So we have a node-based visual thing where you can drag things and connect things up, and it will perform some of the functions, some of the dynamics that you would normally get from a programming language. Now this visual thing that you've created, this gets processed by an internal virtual machine that we have in our program. We could alternatively compile this down to Lua instead and sort of use Lua for this, to implement this thing. We haven't done that because we have some thoughts about, well, performance, maybe if we want to multi-thread this. But I'm not 100% sure. This might just be fierce on our side. It might have been good. It is something that we could try out, try to compile this to Lua instead of to our internal virtual machine. But this visual language actually connects with Lua, so the Lua programmers can create new nodes in this. They can provide a little snippet of Lua code and say, well, this should be a new node in the visual language that does something specific for this particular game, maybe award the player some points or something like that. And then the artists can use that in their visual scripts. So hot reloading, we hot reload the code when the game is running. And as Ragnar said in response to a question, the hot reload, we do that by just running the code again. So if you change a value, like the speed of the jump function here, and you run the code again, the jump function will be redefined and you will get the new value. So there are some things you need to keep in mind when hot reloading. If you'd written your code like in the example above here, and you just ran the code again, here we have a class definition. I just use an empty table. Probably you have some kind of class system, but I just use a table here as a simple representation. If you just ran this code again, then the first line here would create a new player class. So you would get a new global empty table that would be bound to the global variable player. And then when you ran the function definition for jump, you would set the jump function in this new object. So you wouldn't change the old existing player class, which means that all the player instance objects that you have in your game, they wouldn't get the new behavior, because their metatables would still point to the old object, which now no longer has a name, like in _g. But this is pretty easy to fix. You can just do what we do below here. So you write player equals player or this empty class. And this means when you run this code again, this player global, when you run this the first time, you will get a new empty table, but when you run it the second time, it will actually keep its old value, which means that when you get to the redefinition of this jump function, it will change the function in that meta table, which means that all the existing objects in the world will get this new behavior. So this is just something that you need to keep in mind in order to get reloading to work without writing like custom serialized and deserialized code. And there are some more things that can go wrong with reloading that you need to think about. For example, if you have an init function for your classes, that function won't be run again on the existing objects when you reload. So if you introduce a new field in self in your init function, your existing objects will have nil for that field because they won't have run that initializer that sets that value. So you need to think about that. Also, if you store a function in a variable, so you don't access it through this global class, then it won't be rebound, of course, to the new definition of that function. So there are some things you need to keep in mind as a gameplay programmer to keep your code reload friendly, so to speak. The way we implement reloading is we have a custom loader implemented because we want to load from package stuff and so on. And this custom loader records all the files that are loaded in a table in package, which we call package load order. And when you request a reload, we just run do file on all these files that we have stored. And this ensures that we get the files loaded in the same order as during the initial load of these files. And note that if you have require in the files, when we reload and run do file, these requires will actually be ignored because the files will already be in package loaded from the first load, which means that they will be skipped by require. Unless, of course, you require something new, which we haven't seen before, then it won't be in package loaded, so we'll pull it in. So this behaves as it should. So I wanted to go into our bindings, how we bind our C++ code to Lua, because that's something that you can do a bit differently, and I think it's interesting to see what we have done. We use handwritten bindings, and we use C++ 11 lambdas to sort of have everything in the same place, the documentation, the implementation of the function, and the Lua name, and so on. It kind of feels nice to have it all contained in the same place. We use handwritten bindings because we believe that the quality of the API is the most important thing. It doesn't really matter if you can generate the API really, really quickly. Not for our purposes. It's much more important that we have a good API and an API that feels like Lua, not like a thin wrapper over C. And the nice thing with having these handwritten bindings is also that we can, as I said before, we can change the C code without disrupting the Lua API. And we can also do things like if we introduce a new parameter to the C function, we can give that a default value in the Lua API if the Lua function is called without that value. So we can keep backwards compatibility in that way. And also some of these like auto binding things, like if you use template for auto bindings, that will really destroy your C++ compile times. And we want to iterate over our C++ code quickly as well, so we don't like that. For documentation, we use an in-house system that's called ADOC. So we document with the C++ comment, and then this gets auto-extracted to online documentation. And we actually have type, even though Lua is dynamically typed, we actually have type annotations in our documentation. And the reason for that is that we want to be able to have script editors where we can get sort of like a visual assist-like functionality. So the editors can help you with providing the right types and maybe even highlight if you've used the wrong type in some place and so on. So to get some of the benefits that we would get from statical typing. So binding C++ objects to Lua. We have a bunch of objects in our C++ world, and we need to represent them in Lua somehow so that we can talk about them in Lua. Our main goal with creating this binding is performance. We're super performance conscious. And performance in this case means that we want to minimize the creation of garbage. Garbage is expensive. Garbage collection is expensive. Allocating and deallocating memory is expensive, so we want to minimize that. We also don't want to use a lot of like lookups in lookup tables and so on, because that costs as well. An interesting thing to consider is ownership, like who should own the objects. If you have a car in the game, who owns it? Is it Lua that owns it and it gets destroyed when it gets garbage collected in Lua, or is it owned by the C++ side? Well, our view on this is that we want deterministic destruction of objects. When we destroy a level, we want all the objects in that level to be destroyed immediately, and we want to know that we get back the memory. And one of the reasons for this is that we work in very memory-constrained environments. Like when you're targeting a console, you have a fixed amount of memory, and you don't have like this high amount of virtual memory that will come and rescue you somehow. if you run out of memory, you're out of memory, and your game will crash. And often people who build games for consoles, they have maybe like 10 megabytes of free memory or something like that if in their final game. That's sort of their safety zone. So you can't really afford having too much memory loaded. And we want to make sure, and we unload one level and load another one, we want to make sure that we don't have them both loaded at the same time. And our allocation system actually verifies this. So when we unload a level, we have verifications on the allocators that we have really released all the memory. Since leaking memory is so bad for us, since we don't have a virtual memory system, if we leak memory, we will eventually crash on the consoles. So the conclusion from all this is that the ownership needs to reside on the C side, because we need the detailed control, which means that we need explicit create and destroy operations from Lua. So from Lua you say, create this car, destroy the car. Now it's done. So you need to keep track of that in Lua. You can't count on garbage collection. So binding. There are a lot of different ways of binding objects between Lua and C++, and this tries to cover a bit of the different options that you could use. I've used most of these at one time or other in the past. So one option would be that you create a new user data every time an object is returned. So every time we return an object from C++, we create a new user data in Lua. So in this case, the user data are sort of references, and we can have multiple user data referencing the same C++ object. This, of course, creates a lot of garbage, because you get the new user data every time you call something. And tracking lifetime becomes a bit tricky, because you have many objects pointing to the same C++ object. We could store a Lua reference directly in the C++ object, and we would always know, well, here's the reference to the corresponding Lua object. That's kind of neat. It's quick to get to the object somewhat. But then it becomes a bit tricky, like how do these references get released if they're owned from the C++ side? Do they ever get released? And it's also it's not that nice that C++ objects in this case need to be in Lua aware. They need to like hold the Lua data structures, because we like to keep the C++ code isolated and have the Lua as just a layer on top. We don't want the Lua to sort of go into the C++ code too much. We try to avoid that, because we want to be able to. Some of our customers don't want to use Lua. We have some customers that like, well, we want to do everything in C++, and then it becomes sort of bad if Lua is nested down in the low-level code. You could use a weak lookup table based on the object pointer. That's what's recommended in programming in Lua, I think. The only drawback here is that these lookups are potentially expensive. You have a pretty big table if you have a lot of objects. You are pretty guaranteed a cache miss on every lookup in that table. Of course, Lua ref has the same cost, because the Lua ref is a table underneath. Sort of. If you're indexing by numbers, it's a bit better, but still you probably get the cache miss since you have a lot of objects. Finally, you can use light user data, which is just a raw pointer. Then you have the problem you don't have a meta table, so you don't have any type information, and it's tricky to handle lifetime. But we use this anyway, because it's the cheapest. And then we have a bunch of tricks to handle this kind of other stuff, which I'm going to go into now. So meta tables. We don't have meta tables since we have light user data, and this means that we have to call functions explicitly. We can't use the colon syntax to call functions on our C++ objects. Instead, we have to say camera set position. So this is maybe a bit cumbersome, but it's not a big drawback, because we don't have these deep inheritance structures in our architecture. So it's just a bit more to type. And also it actually fits well with the kind of method lookup optimization that you might want to do anyway to increase the speed of your code, especially, at least in certain parts of your code. You want to cache the method lookups. So it fits well with that style anyway. So we don't think this is a big drawback. Then tracking type. We want to make sure that you get a type error if you try to use like a camera as a light or a camera as a sound. You should get some kind of error. So how can we do that without using meta tables? Well, we do that using the C objects themselves. So in the C objects, we start every object on the C side with a type marker. So it's just a unique number that is like the first int of any object's memory. And that means that we can test this when we get some argument from Lua, we can look up this marker value, we can just check the first unsigned in the object and see if it matches the expected value, and if not, we can give a type error and say, well, this was not the type I expected. So lifetime, that's even trickier. I mean, ideally, you have to ask, since Lua doesn't own the objects, they are created and destroyed with specific functions, you need to ask, well, what happens if we try to use an object that has been destroyed from Lua? What we would want is we would want a Lua error that says, well, you're attempting to use a destroyed object or something like that. But this can be a bit tricky. I mean, we don't have any general weak reference mechanism on the C++ side. So that memory that object occupied and that user data is pointed to is now used by something completely different. So what do we do? How can we handle this? Well, what we do is our hack sort of solution to this is when we destroy an object like the camera, we clear out this marker field. So this means that if you, in most cases, if you try to use an old object that has been destroyed, you will either see this 0 marker because we have cleared it out, or you will see some other data because some other object has been placed in that position in memory. Which in either case you will get a type error. Of course, this doesn't work 100%. There are some situations where it could fail. For example, a new camera object could have been created in exactly the same place. And then we would still see a camera type field and we would think that, oh, here's our camera, nothing is wrong. Or the memory could have been freed altogether and returned to the system so we could get an access violation. But both these situations are kind of rare in practice, and we don't actually need this to work 100%. I mean, this is, if you're using a dead object, that is a user error. I mean, it's nice. I mean, you shouldn't make errors, but if you can catch the errors like 99% of the times, that's usually good enough. Because if you don't get it on this run, the error, you might get the error on the next run. So it's actually not, I mean, it's scary, but it's actually not as bad as it might seem. So this explicit creation deletion, that works pretty well for big objects like a car. But for really small objects like a playing sound or a particle effect, you don't want to explicitly create and destroy it every time. So for these kind of short-lived items, we want to have some sort of weak referencing system. So for these items, we tend to use IDs, and IDs are just integers that are kept track of in each system. So the sound system, for instance, keeps track of IDs for all playing sounds. So when you tell the sound system to play a sound, you get back some ID, and then you can ask later with this ID, is this sound still playing, and use that ID to change its volume and so on. These are just ints, so you don't have any type information, so you don't know if you take an ID from the sound system and send it to the particle system, you won't get an error, but pretty good anyway. Then we have some special objects where are so important that we want both weak referencing and type information. And those are our like main game objects. They are called units and entities, and these are like your car, your player, your house. Pretty much every object in the world is one of these objects. And they are so important that we want type errors, but we also want this weak referencing system. So we can't use ints because then we have no type information, and we can't use light user data because then we don't have weak referencing. So what we do in this case is we hack the light user data. So we take advantage of the fact that in our game all our pointers are 4-byte aligned. That's the way our allocators work. We never allocate off a 4-byte boundary. And this means that all light user data that represents ordinary pointers will have 0, 0 in the last 2 bits. I'm assuming 32-bit system here. If you have 64 bits, then it's great, because then you have more bits to play with, so you can store more secret information in the pointers. But on the 32-bit system, we pretty much have to do with these 2 bits. So they are always 0 for an ordinary pointer, and that means that for these special objects, we can use a different value to indicate that this is one of our special objects. So we use 0, 1 for our units and 1, 0 for our entities. So just 2 different types of game objects. And then we can use the remaining 30 bits for the ID value. So that's just an integer that works like our other integer IDs. Then we have another trick, temporary objects. Now, if you in a game, you typically have a lot of vector math, like positions, speed, and so on. You have a lot of calculations like that. And these calculations can really generate a huge amount of garbage, an enormous amount. You can easily create 10,000 vector 3 objects just by moving around a bit of sprites in your game or whatever. And this will really, really hurt your performance. But we want to have this nice syntax. We want to be able to type arithmetic expressions. So how can we do that without generating all this garbage? So we use a pretty big hack here as well. So our solution is these temporary objects. When you have an arithmetic expression and you get these intermediate temporary objects, they are temporary. They can only be used in the current frame of the game. So it's invalid for you to take the result. To take the result of an expression like this and use it the next frame. You're not allowed to do that. It's a bit weird. So how do we handle that? Well, on the C++ side, we have a big ring buffer that is statically allocated. That's the big ring buffer of memory. And here we store all these temporary objects. So we store a marker data for all our different kinds of temporary objects. We have quaternions, vector 3s, and stuff like that. And this means that we can represent them by light user data just pointing into this buffer, just as other objects. But we don't have to explicitly free them because they get freed automatically every frame. They get invalidated and freed every frame. And the way we free them is that when we flip the frame, we go through all the objects that were created in the previous frame, and we change the marker values in this ring buffer to represent sort of a stale version. So this is something like a type field that indicates this came from a previous frame. You should not be using this. And if someone tries to use a value that comes from an old frame, unless it's from a very old frame, so it's been overwritten because it's a ring buffer, so eventually things will be overwritten. But again, most of the time, if people try to use an old value, they will get a type error that says, well, you're trying to use a vector 3 that comes from an old frame. That's bad. You can't do that. So what do you do if you need? I mean, obviously, you need to save the results at some point. You want to use stuff in multiple frames. So then we have a boxing system. So we box the value in the full user data if you need to store it from multiple frames. So then you have to explicitly create a box or store it in an existing box. And this will generate garbage because now we're creating a full user data value that will be garbage collected. But you have control over it. You know when you create these objects. You don't create thousands of them just because you're doing some calculations. So all of this is really strange. I mean, if you never encountered this before, it's really strange. I'm using my variables get invalidated the next frame. It's super strange, but it really gives you the performance you need. It's hard to do something. It's hard to get reasonable performance without doing something like this. I don't know of any other way of doing it. So we do it. You saw that we had operator overloads in the arithmetic expressions. You might be wondering about that. Since we're using light user data, we can't have individual meta tables for the vector 3s, but we can have a shared meta table for all light user data. So we can actually store these arithmetic operators in a shared meta table for all light user data, and then we can check the actual type in the operations. So that way we can get arithmetic operations while still using light user data. So I'm going to go into a bit more performance things. Garbage collection. Games are kind of special compared to a lot of other applications, that they are soft real-time applications. So garbage collection stalls are not acceptable. And so ideally we want to spend a constant time garbage collecting every frame. We want to use incremental garbage collection, but more than that, we want the amount of time we spend on incremental collection to be the same in every frame. Also, garbage collection is expensive, as I said before, so we have the philosophy that our APIs should never force garbage on the user. If you call an API function, it should never generate garbage unless you want it. You can like enclose returned values in a table if you want to for convenience, but we shouldn't return a table and force you to generate garbage. So you should be in control over garbage generation. That's why we have this all the stuff I talked about before, that we use light user data for almost everything. So I don't know if you've thought about this, but if you start to think about how expensive is garbage collection, what is the cost of garbage collection? Does it depend on how much memory you're using, or what does it actually depend on? And if you assume you can actually solve for this and get a kind of nice result. If you assume that you have a steady state, so you have a resident memory that is M, that is constant. You generate the same amount of garbage, G, every frame. You sweep the same amount of memory every frame, S, and you take F frames to complete the sweep. Then this equation will hold that you completed a sweep in F frames. This is the total amount of memory that you've swept. And in that time, you must sweep all the resident memory plus all the garbage that was generated in those frames. Now assume that the amount of garbage that you can accept is some fraction alpha of your resident memory. That's kind of a reasonable assumption to make. You can say, well, we accept 50% garbage. We use 10 megabytes of memory and we accept to have 50% overhead from garbage. Or we accept 10% overhead, or depending on how chic you feel. Then you can solve for this, put this into this equation, and the nice thing, the kind of interesting thing, is that the resident memory falls out of the equation. So it really doesn't matter. The amount of resident memory you have doesn't really matter for the cost of garbage collection. It's directly proportional to the amount of garbage you generate per frame, and this factor alpha, which is the overhead you accept. And as you see, if you try to force this down to be really low, which you might want to use on a console where you have very little memory, you get punished very hard. Like if you say, well, I'm going to only have 1% overhead, then you get a factor of 100 here, so it gets pretty expensive. So you pretty much have to accept like 30% maybe overhead in order to not get an insane value there. But other than that, the cost of garbage collection is proportional to the amount of garbage you generate. And of course, the cost of allocation and deallocation of memory is also proportional to the amount of garbage you generate. So again, that's why we want to keep garbage generation as low as possible, because everything depends on that. So to drive how we do our incremental garbage collection, we have sort of a heuristic algorithm for that. So as I said, we want to spend the same amount of time sweeping garbage every frame. We don't want to sweep too much, because then we're wasting performance. We never want to do that. We don't want to sweep too little, because then if we're generating more garbage than we're sweeping up, then eventually we will run out of memory. So we want to tune this, which is tricky, because we don't know what the game is doing, if it's generating a lot or a little garbage. So the way we handle this is there is a variable inside Lua called the estimate, which is not normally exposed in the API, which estimates the value M in the previous slide, the amount of non-garbage memory that you have. So we modify Lua to expose this so that we can create an estimation of our current value of alpha, the amount of overhead we have. The total bytes of allocated divided by estimate minus 1. And then we sort of compare that to our target alpha value, how much overhead we're willing to accept. And if it seems too high, we turn up the garbage collection a little bit and try to get closer to the value we want to have. This is completely heuristic. It's completely, it's hand-wavy thing. It's controlled feedback loop that we've kind of tuned to get to work. It seems to work nicely. But it's kind of tricky to do this in a good way, since you don't know until you've finalized a full sweep how much memory you swept up during that sweep. So, but this is what we do. So LuaJIT, we use LuaJIT. It can give you huge performance boost. It's a great just-in-time compiler, one of the fastest that exist for any language. But there is a problem with it from our perspective, and the problem is that if you have a multi-platform game, you have some fast platforms, typically PCs. Then you have some slow platforms, typically mobile phones and game consoles. Now the problem here is that you would really want to speed up your code on the slow platforms. But on consoles and on iOS, you're not allowed to JIT your programs. You're not allowed to run a just-in-time compiler. And this means that on the platforms where you really need the performance, you can't get it. So it's kind of, in a way, it's kind of pointless. I mean, we can speed up the PC, but the PC is already faster than the other platforms. So if you're targeting multiple platforms, JITting really doesn't buy you that much. If you're targeting just the PC, it's good because then you have the JITting and you can use it. But still, we still use Lua JIT because even in interpreter mode, it's faster than regular Lua by about 30% in our measurements. So it's still worth using for us. We don't use Lua JIT FFI. Lua JIT FFI can theoretically give you a performance boost by bypassing the stack manipulation that you usually have in your API bindings. But in our tests, we haven't seen that big performance improvements. Part of that is because a lot of the time, games today are memory bandwidth limited rather than CPU limited. And the problem with FFI is if you don't have just-in-time compiles, FFI has worse performance than regular stack manipulation. And we want to keep the platforms kind of similar, so we don't use FFI. So slightly scary thing for us is a sort of divergence that is happening between Lua and Lua JIT. Lua is at 5.3 now, Lua JIT corresponds roughly to 5.1. So the divergence is kind of increasing, and what will happen there? Will we have two separate languages? Will Lua and Lua JIT go separate ways? Is that a problem? Maybe, maybe not. Interesting things to consider for the future. Another slightly scary thing, if you follow Lua JIT, you've probably seen that Mike Paul, who used to be like the single genius behind Lua JIT, has stepped down and he won't continue supporting the project. Right now, the sort of leadership of Lua JIT is a bit uncertain. Will someone step up? What will happen? What direction will it take? We don't really know. I mean, this doesn't hurt us immediately because Lua JIT is good as it is. We can use it as it is for now and probably for many years to come without running into any big issues. But without a clear leadership, it might get outdated at some point. It might get outrun by like JavaScript just-in-time compilers, for instance. Still, Lua JIT is still ahead of them as far as I've seen so far. But it might, something could happen there. So it's a bit scary. Even more scary is multi-threading Lua gameplay code. So there's no obvious, real good way, like, oh, this is what we want to do, this is a super nice way of doing this. But it will soon become a necessity. We are already seeing it. I mean, we're targeting some high-end games. It's a bit different on default because you have fewer processors on mobile hardware. But on PCs and Xbox Ones and PS4s, you typically have 4 cores. I mean, that's more or less the standard nowadays. And as we are aggressively multi-threading everything on the C++ side, Lua becomes more and more the bottleneck. That's Amdahl's law. Like your serial part becomes more and more the bottleneck the more cores you have. And we can definitely see the pressure on the main thread increasing. If you look at our profiler, you can see that a huge chunk of each profiled frame is Lua running on the main thread. So we want to do something about this, but we're not sure exactly what. Multi-threading gameplay code in general is hard because gameplay code tends to be sprawling. It's easy to multi-thread code, like here are my animation updates. I have 1,000 animated characters and I need to animate them. It's super easy to parallelize. But gameplay code tends to be like, get this character's position over here, get this character here, do a raycast there, move something here. It's touching a lot of different places. And if you're going to use like locking, then you have to lock all these things. It doesn't really work. So it's tricky to multi-thread in general. And also, since Lua is not multi-threaded in itself, to multi-thread in Lua, we have to have a separate Lua state on every thread. That's the only same way of multi-threading it. And that will increase our memory use a bit, depending on how much we mirror to each Lua state. That depends a bit on how you do things. And you also run into these questions, which I guess is what Default run into, and which made them merge their states at some point, is how do you synchronize state between Lua states? What state lives in each separate Lua state, and how is that synchronized? So there are some different multi-threading models. Shared memory unlocking, which is what you usually use like when you multi-thread C++ code. I think that's way too complicated for using gameplay code. I mean, we can't expect gameplay programmers to use that in any sensible way. It's just too hard. It requires language support as well if you're going to synchronize access to Lua objects. I'm not sure how that would work. But anyway, I think this model doesn't work. Software transactional memory, I've just written because actually I don't know enough about it. Maybe it'll solve our problems. I don't think so, but I don't know enough about it, to be honest. So I just put it up there. Maybe someone else knows more about it. Then it's the actor model, which is what I think is the sanest. It's the multi-threading model that is most easy to grasp your head around. I mean, Erlang has been doing it successfully for kind of a while. It's similar to what Default are doing, except they're not actually multi-threading, but it's the design of it is very similar, and it's easy to reason about. You know what you're doing. You won't into deadlocks or other strange multi-threading things. A drawback of it is that if you try to split your algorithms up over multiple messages, it can become kind of messy. If you have to send a message to this thing there, wait for the result, send a message to this thing, get the result from that, then I merge those two results and set it to some other thing. You have to do several asynchronous calls and merge the results to get something that you can use. So it becomes kind of not as nice to read the code as you would have from regular iterating code. So one alternative that I've been sort of toying with in my head is to use the actor model but have sort of an implicit messaging model. So this is just an idea. So the idea is that you would write the code for your actor as usual. You would write iterative, normal Lua code. But whenever you called a function on an actor that was owned by a different thread, so it's not owned locally, so you can't call it directly, what would happen is that we would suspend your coroutine. So all of the updates would run in coroutines. We would suspend that coroutine, and the thread in the Lua state would continue to update the next actor. Then after all updates have completed, we can take all these calls that were made to foreign states, and we can process them, batch process them, send the results, synchronize them, do this thread synchronization step, get all the results, and then when we have the results, we can go back and resume these suspended coroutines. So this way you would kind of get an actor system, messaging-based system, but still have code that looks like your normal iterative code. Maybe it would work. So we need to address this in the future. I'm not sure exactly when this future is going to come, when we need to address it, but our plan right now is we'll still have a main thread. We won't go all out threading because I think the simplicity of having a main thread is still really valuable. So we still want to have that, but we want to combine it with an actor model so that users who want to do a lot of Lua processing can use multi-threading. So we want to offer them the possibility. For people who don't need it, they can continue to do everything on the main thread and don't worry about it. But for the people who need it, they should have some option. But we're still a bit undecided about should we be explicit with message passing or do this implicit thing. The nice thing about this implicit thing is kind of allows you to write code as you did before, but you have less control, you have less knowledge of what is really going on behind the scene. We're kind of hiding that for you, and that's not always a good thing. You can get sort of strange performance bottlenecks that you don't understand because you have a ton of message passing that you don't see going on in the background. But we're still trying to figure that out. So that was all I had. So we have 10 minutes maybe for questions. If you have anything you're wondering. Yes.
A comment. I think the implicit messaging sounds really good.
Yeah.
And you should try going through it because it's implicit messaging. build the built-in Lua ID, right? In the engine, in the editor.
Lua ID, what do you mean by that?
I mean, you can write code, you will get syntax highlighting, etc.
Yeah, yes, we have.
Okay, so the question is, if you want to use an external editor, something like Sublime Text, etc., will the editor detect code changes when I code reload?
Yes, I think so. The editor, which editor?
Stingray.
Stingray.
So if I run the game, right, I change.
Yeah, I'm not 100% sure because that's in like the editor part. I'm more on the runtime core stuff. I'm not sure. I would hope so. Yes.
You don't need the implicit. I mean, if you've got the explicit communication, just wrap it in a function.
Yeah, you can do that.
And then you get the benefit of both sides.
Yeah.
And without the weirdness of doing the implicit.
True. Yeah.
But it seems like multi-threading is something that pops up again and again. It's a big question mark on what do we do here.
Yeah.
Has anybody actually run a multi-threaded Lua? I know there is locking.
I mean, there are projects. Oh, you mean like in a single Lua state?
Yeah. So I mean, in theory, there's lock and unlock that you could implement, that you could define. I just don't know. Has anybody ever tried this? Because I've seen it and gone, oh, that's interesting, but
The Lua project used to do that, but it turned out it's sort of like you're not with the Python guild, where you only really get to do processing when you're in a C function. So it's not that useful. There was originally when lanes came out, there was a whole web page back comparing sort of message passing versus using the lock, which had benchmarks and a lot of things about it. If you need to look something up.
Yeah.
But the lanes approach, like multi-process, does end up much better.
Yeah, I think that is better, and I think, from what I read, people are not that happy with the GIL, the global interpreter lock in Python.
Locking kills you.
Yeah.
Immediately, I mean, and versus it doesn't scale.
And to be frank, when we consider multi-threading, Lua is only part of the problem. I mean, we have Lua, then we have all these engine systems. And Lua calls out into all these different engine systems. And if all those calls are going to happen from different threads, we need locking and thread safety there as well. So, yes?
Is the code that really that's programming, or is it a small part of the game logic? For instance, in the previous talk, we were saying when they start this kind of algorithm,
Yeah.
it's consuming a lot of CPU. That would be the kind of thing that we should be ready.
Yeah.
Basically, when you run that, you don't take all the big things.
Yes. Yeah, I see what you mean. And I mean, definitely when you have this kind of low-level stuff, like an A-star algorithm or stuff like that, there's nothing that prevents you from writing that in C++ and adding a Lua API. So we have, most of our customers are source customers. They have the full C++ source code, and they are able to do that. But in my mind, what happens, if you look at what happens, this is not my total field of expertise because it's mostly my customers that do this, but when you have performance problems, the main source of performance problems is badly written Lua code. Like you have badly written code that generates a ton of garbage and does processing that it shouldn't do. That's like, if you look at like if I get to a new project and I see bad performance, that's what I expect. People don't really know how to optimize their Lua code, and some people think if they come, this especially happens with C++ programmers that are used to programming games in C++, and then we say, now you should use Lua. Then they write really bad Lua code, and then they say, oh, now it's slow because I use Lua. And then they translate that really bad Lua code to C++, and they don't get the performance improvement, and they get confused. But so mostly it's Lua performance problems. Now, if you take the time and sit down and go through that, which you can do, and like cache things in local variables and do all the good stuff you can do with Lua, make sure you're using memory wisely and so on, then you can get pretty good performance of Lua, but then at some point, when you do all that good stuff, you still run into a limit. And the cases where you have this like low-level processing that you can move to C, that's usually, I mean, you might have a few of those, but usually that's not the problem. Usually, as I've seen it, the problem is that once you've optimized, removed the obvious bad stuff in Lua, you just have a bit too much code. Like, so it's not single things that you can pull out and optimize, in my experience.
So it's basically you think that the approach that they do is broader with web workers. Like if you cannot have something that push one operation to any feature, then you get the results.
Yeah, you could do that maybe, but I mean that would be. Yeah, but if you're talking about futures, you're talking about operations that complete over multiple frames, I guess, mostly. And mostly that is not such a big problem. Mostly we already have things to deal with that. The bigger problem is the things that need to complete in this frame. How do we solve that? How do we do all the things that we need to do in this frame? Yes?
Do you have any kind of profiling to see where your program is generating damage?
Yes, we have a profiler built into the engine that sort of streams. It basically just records events like start and stop with time flags, and then you can stream that over the network so that you can run it on a phone, for instance, and get it in another application and get a nice view of it. And with Lua, it's nice because, as someone said, it's I forgot the word, hackable. I mean, you can override things. So we actually have a dynamic Lua profiling option, which means that you can override an existing Lua function, insert the profile calls at the start and end of it, and then call back to the old definition. So we have a tool for that. At least we used to have, I'm not sure if it's used anymore, but where you can sort of drill down into the Lua code. You insert a profiling option, you see it's slow, then you insert more profiling code, sort of live drill down into where the time is being spent in Lua.
Is that instrumenting the data automatically, or do you need to add the code? Okay.
I mean, we had an automatic instrumenting for it that allowed you to sort of with one click, but I think that was someone's like hack day project that they did. I don't think that's part of the product, but right now. But it's not that hard to do. I mean, you can just write some code that does it and inserts the preamble and postamble, and then calls out to the old Lua function definition. So it's a pretty easy thing to do. But I don't think we have it in the product right now. All right, thank you.